Hi everyone, we're on our last lesson and we're going to talk about composite shapes, surface area and volume of composite shapes. What does composite mean? A three-dimensional composite shape is an object that is made up of two or more basic three-dimensional shapes. So we've learned about prisms, cylinders, cones, pyramids, and spheres. Now we're just putting it all together in any number of combinations. So you're going to get some really weird looking shapes, right? Or you might even get shapes like, hey, I've seen that before in real life. When you're calculating the total volume of a composite shape, very straightforward, volume. Determine the volume of each basic shape, then add up all the volumes. That's it. When you're calculating the surface area of a composite shape, be careful. Be very careful. If one of the basic shapes rests on top of another, you will not count the area of the overlap at all, because remember, surface area, basically one way to think about it is that is it covered or can you touch it, right? Pay attention to the context of the problem. What is the problem telling you? Sometimes composite shapes are resting on the ground, so we will not count the bottom of that shape. So common sense things like that. If it's resting on the ground, you won't count that surface area because you can't touch it, right? Let's try a two-dimensional composite shape as a warm-up. Determine the perimeter and area of the two-dimensional composite shape. Perimeter. That's just the distance around a shape. That's 6 plus 4 plus 9 plus 5. Perimeter equals 24 centimeters. How about area? Area total equals area of the rectangle plus area of the triangle. Much like we do for three-dimensional shapes, I'm going to do this for two-dimensional shapes. Break it up into shapes that you know. This has to be 4 centimeters, the height of this triangle. Well, what is this base of the triangle? Well, I'm going to scratch this out. If this top part is 6 and this big part was 9, then this has to be 3 and this smaller part has to be 6 for a total of 9. Okay, and then now the area of the rectangle is length times width, which is 4 times 6. Area of the triangle is base times height divided by 2. That is 3 times 4 divided by 2. 24 plus 12. Oh, 24 plus 6, and that is 30. 30 square centimeters. Okay, let's do our first composite surface area and volume problem. And the hard ones have a story behind them or there's context to it. I could just give you a shape, composite shape, and say calculate the surface area, calculate the volume. This one I'm going to give you a story. You are applying sealant on a monument that rests on the ground. So it's on the ground, right? So imagine, right here's the ground. It's a monument somewhere in the park. Who knows? Okay, so it's resting on the ground. How much sealant will you need to completely cover the monument twice? So 2 times, right? 2x, 2 times. Okay, so this is a stone monument and you put sealant on it so that the stone lasts longer. It doesn't wear as much, right? So we need to think surface area. How much sealant? So I'm thinking surface area. First, I'm going to break it up into the pyramid. But I'm going to say no base because I'm not going to apply sealant to the base. That doesn't make sense, right? So the pyramid, in this case, is just 4 triangles. So I'm going to do this sort of analysis before I put everything together. So I have 4 triangles. Surface area equals, here's one triangle. I have the base, which is 9 feet. And I have the height of the triangle, which is 11 feet. So this one's right. All the numbers are here for you, straightforward. Base times height. Oops, sorry. Let me do this. 4 triangles, so 4 times base times height divided by 2. since I have 4 triangles. So surface area equals 4 times, what's my base? 9 times height, which is 11, divided by 2. Surface area equals 198 square feet. Put a box around that. That's my triangular, that's the 4 triangular faces, right? 4 triangles. Now I need a rectangular prism. So you see the bottom part is a box or a rectangular prism. Okay, and then this one, no top, no bottom. No bottom, obviously, because it's resting on the ground. No top, because the pyramid is on top of the top of the rectangular pyramid. So I just basically have 4 rectangles, or I'm just counting the surface area of the lateral faces. So that surface area equals 4 times 4 rectangles. So 4 times length times width. Surface area equals 4 times length, which is 9 times 10. And so surface area here is, of all 4 rectangles, is 360 square feet. Okay, what's the total surface area? I'm going to take the surface area of the 4 triangles of the pyramid and then the 4 sides of the rectangular prism. So 198 plus 360. I get 558 square feet, but I want to cover it twice, right? I'm coating this monument twice with sealant. So I go 558, 2 times 558 square feet. I get 1,116 square feet of sealant to cover, to cover twice. Okay, there we go. Next one, the monument is made of solid marble. Determine the weight of the monument if the density of the marble is 160 pounds per cubic foot. So this cubic foot part, this is a volume. Remember, density is mass divided by the volume. Mass divided by volume. Mass divided by volume. I have this value here, which is the mass per volume. I just need to find the volume. Okay, so let's so remember, for volume of composite shapes, it's very straight up. Just what is the shape of a component piece? So I have a pyramid, so I need the volume of a pyramid. So let's look at my pyramid here. So I need volume, and volume equals area of the base times height divided by 3. I need this vertical height. So if I draw the center of the base of the pyramid, I have this right triangle right here. I need this height. What is that height right there? So I'm going to pull that away here. So I have, this is 9, so this part right here has to be 4.5. 4.5. And then this is the height I'm looking for, and this is 11 feet. Okay, do a little bit of Pythagoras here. 4.5 squared plus 8 squared equals 11 squared. And then rearrange everything. I'm going to just skip a step here. I get the square root of 100.75. And then so now I'm going to take the area of the base, which is 9 times 9, times the height, which is square root of 100.75 divided by 3. And so I get a volume of 271.0106. Let me put it out to a couple digits for accuracy, cubic feet. So that's the volume of the pyramid. Let's find the volume of the rectangular prism. So rectangular prism. And remember, volume, just straight up. I see the shape, apply the formula. Volume equals area of the base times the height. That's it. Height of the prism, right? So volume equals area of the base is 9 times 9, and the height is 10 feet height. That's the height of the rectangular prism. So volume of the rectangular prism is 810 cubic feet. So volume total of the monument is 271.0106 plus 810. Volume total equals 1081.0106 cubic feet. Okay, let's box that. Density, let's write this out, equals mass divided by volume. So the mass, we said, is 160 pounds per cubic foot of volume. And if I multiply it by this value here, 1081.0106 cubic feet, I'm going to have the cubic feet values cancel out, and I can find the total mass of the marble in the monument, and I get 17,000, rounded to the nearest 10, 172,961.7 pounds. That's the total mass of marble in the monument. All right. Okay, a couple more to go. Next page. I'm going to do one more example with some different shapes, and I'm going to let you do a you try. Next page. Example, a submarine-launched ballistic missile. The shaded object to your left is housed inside a sealed container that is a right cylinder. The height of the sealed container is 48 feet. Calculate the volume of the missile. So looking at my components, the missile, this is the shaded part. I see a cone, so the volume of the cone plus volume of the cylinder. So let's pick off those values here. So for the volume of a cone, I have my radius. We said the total height is 48 feet, so we need to do a few things here. 48 feet. So the height of this cone, therefore, would be vertical height, 48 minus 32, 48 minus 32, and that is 16 feet. Okay, so I got everything I need for the volume of the cone. How about the cylinder? This, because the cone is stacked, the radius of the cylinder here is also 3 feet. And I have the height of my cylinder right here. So I have everything I need. So volume of the missile equals volume of the cone is pi r squared h divided by 3 plus volume of the cylinder is pi r squared h. So that's pi times 3 squared times h of the cone. Height of the cone is 16 feet divided by 3 plus pi times radius of the cylinder is 3 squared. Height of the cylinder is 32. Volume of the missile is 1,055.6 cubic feet. Right. The skin of the missile is made of high tensile strength steel and covers the entire missile except for the bottom. There is no steel covering the bottom of the missile to allow rocket boosters to ignite and propel the missile. What is the surface area of steel in the skin of the missile? Okay, surface area of the missile, so let's look at the component parts, equals So I see a cone. Let me write it out in general terms. And I see a cylinder. But let's be careful. Read the question. Surface area of the cone. See how the cone, the base, is stacked on top of the missile? So right here. I'm not going to count that circle base for the cone. So normally it's pi r squared plus pi rs, but I'm not going to include this because there's no surface to touch, right? It's not exposed. So surface area of the cone is just the lateral surface, which is pi rs. And then the surface area of the cylinder, the top of the cylinder, same reason why we don't consider the bottom of the cone. We're not going to include that. Okay, so normally it's 2 pi r squared plus 2 pi rh. We're only considering the lateral surface of the cylinder. So this is not considered because the bottom of the cylinder does not have high tensile strength steel because there are boosters there. So what do we have left? We have pi r, we have 2 pi r squared. 2 pi r, so the lateral surface, and we have the height. And I'm going to call it h2. So this is height 2. So I can distinguish between height of the cone, height of the cylinder. Let's plug everything in. Pi times the radius of 3. The slant height, we need to calculate this. So if I take my cone, if the radius is 3, and there's my vertical height, the vertical height is 16. What is the slant height? So I need to go like this. Slant height 16, 3. 3 squared plus 16 squared equals s squared. Do all the work, I get s equals square root of 265. And then so the slant height is square root of 265 plus 2 times pi times the radius is 3. Let's fill it in for the surface area of the cylinder. 2 times pi times 3. And then the height of the cylinder is 32. And then crunch all those numbers. What do I get? What is the surface area of the highest tensile strength steel? 756.6 square feet of high tensile strength steel. Okay, 756.6 square feet of high tensile strength steel. Alrighty, done with that one. Pause it here, give this you try. This is a challenging one. How much paint is required to paint the outside of the water tank twice? So I have, basically if I analyze this, I have a cylinder and 2 hemispheres. And you could do this a number of ways. You can calculate things for each hemisphere. Or I have a cylinder, depending on the way you look at it, and 1 sphere. Because if I put the 2 hemispheres together, I get 1 sphere. So how much paint is required to paint the outside of the water tank twice? So I need the surface area. Surface area of the water tank total equals surface area of the cylinder. Let's do it in general terms. Plus surface area of 2 hemispheres. Okay, surface area total. What do we got? Let me put this in general terms first. The cylinder, I'm just considering the lateral surface. So it's going to be, normally it'd be 2 pi r squared plus 2 pi rh, lateral. This is the lateral part. Okay, this is the lateral part, but then we don't want the 2 circles, so I'm going to just write out the lateral part. So 2 pi rh, and then the 2 hemispheres. Okay, remember 2 hemispheres. Let's call it the simple way. Let's call it 2 times 3 pi r squared. But remember, this 3 includes the circular bases, so I'm going to get rid of that. Right, so it should be 2 times 2 pi r squared, which becomes 4 pi r squared. And if you're considering just 1 sphere, the surface area is 4 pi r squared. Anyway, okay, so that's what we arrive at. Let's plug everything in. 2 times pi times r The radius is the radius of the sphere. That's the diameter. So the radius, r, equals 3 centimeters. So 2 pi times 3 times the height. It's slanted. I mean, it's on its side, so that's still the height of the cylinder. Oh, sorry, this is the cylinder. My apologies, right? So the cylinder, if I back up here, the radius is 3 because the radius of the hemisphere is also the radius of the cylinder. So that's 3. And then the height is 8.5 plus, now let's do the two hemispheres, which is 4 pi times r, radius is 3 squared. Add all that up, or multiply and add 160.2212 square centimeters. Oops. This one, sorry, my apologies. Well, 160.2212 plus, and then the hemispheres are 113.0973. The total surface area is 273.3185. And then if I paint twice, I multiply this by 2. So 2 times 273.3185. I have 546.6 square centimeters of paint to cover. So that much paint to cover twice. Okay, oops. Right there. Okay, that's the surface area. Let's do the volume. You'll fill the water tank 2/3 full. How much water will you use? So volume of the cylinder. So let's calculate volume of the cylinder and volume total equals volume of the cylinder plus volume of two hemispheres. So that equals volume of the cylinder is pi r squared h. So straightforward, just straight up calculate the volumes. Volume of the two hemispheres is 2 times 2/3 pi r cubed. So pi times the radius is 3. The height of the cylinder is 8.5. Oops, 3 squared times 8.5 plus 2 times 2/3 pi times the radius of the hemisphere. It's 3 cubed. Okay, and then I end up getting 240.3318 plus 113.0973, and that equals so 240.3318 plus 113.0973, and I get 353.4291. And then remember, folks, I want to fill it 2/3. So if I go 2/3 times 353.4291, I end up getting 235.6 cubic centimeters is my tank 2/3 full. That's it. Okay, this is a cool little video on optimization of shapes. Really cool, fascinating topic if you're getting into mechanical engineering or just engineering in general. Good spatial reasoning drills to do is thinking about the ingenious design of the aluminum beverage can. Why is it a cylinder? And there's more to it just than a simple cylinder. It's a cool video, so scan the QR and take a look. That's it. Get some practice.